Chapter 5 is on eigenvalues and eigenvectors. Now we need to solve a new problem, and the new problem to solve is how to solve ax equals lambda x, where x is a vector, A is a matrix, and lambda is a scalar. Can be real, can be complex. Again, the matrices and the vectors can also be real or complex. So we want to solve it. By diagonalizing the matrix A. Echelon form, the row reduced echelon form changes where we do elementary row operation, changes eigenvalues. So we do not want to take that approach. Determinants that I told you that you need to study on your own lead to a formal solution of the polynomial. So determinants lead to a formal solution of the polynomial A minus lambda I. And you may be wondering where we get this A minus lambda I. This we can write as, if I put an identity matrix here, nothing changes. And when I take this term on the left side of this equal to sign, so I have ax minus lambda I x equals 0, or this implies x I can take out on the right side. I can't take out x on the left side because matrix multiplication is not defined like that. So I have a minus lambda I into x equals the 0 vector. Okay. So this is what he's saying. Determinants lead to a formal solution of the polynomial a minus lambda I, whose roots will be the eigenvalues. Okay. And just to reiterate the fact, eigenvalues are only defined for square matrices, or actually the determinants can only be computed for square matrices. So all matrices to be considered in this chapter, from now on, actually in this chapter, not from now on, in this chapter, because in chapter 6 we are going to go back to the rectangular matrix, and then we are going to see what is the counterpart of the eigenvalue problem for a rectangular matrix. So that's the superset eigenvalue problem that we are discussing in chapter 5 is actually a subset. All matrices to be considered in this chapter will be square. So one of the applications of eigenvalues is to the solution of ordinary differential equation. Ordinary differential equation, which is ODE. So let's consider dV by dt. So this is a coupled differential equation, is equal to 4V minus 5W, and dW by dt equals 2V minus 3W. The initial conditions are V0 equals 8. So this is at t is equal to 0. I hope you know this notation. And W0 equals 5. These are the initial conditions. Initial conditions. So in an initial value problem, unknown is specified at t is equal to 0 by the given initial conditions, initial values 8 and 5 in this case, 8 and 5 in this case, and you are asked to, and the problem is to find, and you are asked to find V of t and W of t for t greater than 0. Okay. So let me write this problem in the matrix format, and let's define U of t. So whenever I put triangle on the equal to sign, this means it's a definition. So U of t is some V of t and some W of t. U of 0 is simply 8 and 5. This is the value of V of 0. This is the value of W of 0. And A is based on these. So A, we say, is 4 minus 5 to minus 3. So if that is the case, so I have du of dt equals A times U with, so I've dropped the t, knowing that this is the function of t, with U equals U0 at t equals 0. So just to recap, although you have already taken a course on differential equations, this is a first order. So this is a first order linear. This is the first order. Why? Because no higher order derivatives appear. No higher order derivatives appear. So it's the first order linear in the unknowns. Linear in unknowns. Unknown is U. Linear, constant coefficient. Why? Because A has constants. Constant coefficient because elements of A do not depend on T. Constant coefficient differential equation. And from your uh, and from your differential equations course, you know that, and from your differential equations course, you know that from your differential equations course, probably that the one that you took in the last semester, you know the solution of a first order differential equation. And just to recap, for the scalar case, du over dt equals some au, where u equals u naught, and the solution for this is an exponential, because exponential solutions actually satisfy this differential equation. So if u is some exponential, d over dt of u would be an exponential. An exponential is there, so obviously an exponential satisfies the differential equation. So u of t is some EAT u of z. And we also, and probably you also saw over there, okay, depending on this value of a, depending on this a, your solution is either stable, unstable, or neutrally stable. So let me define those again for you. So the solution is unstable. Unstable means it's going to go without bounds when a is greater than 0. So solution is unstable for a greater than 0 because EAT tends to infinity. Okay. And solution is neutrally stable. Its solution is neutrally stable for a equals 0 because EAT remains bounded. And finally, solution is stable. Solution is stable for a less than 0 because EAT approaches 0 as t tends to infinity. As t tends to infinity, remains bounded as t tends to approaches 0 as t tends to infinity. Okay. And if A is complex, what happens? So if you have done your second order equations probably you've done that in the circuits course, probably in the first or the second course that you're taking right now. Over there, the solution this A is a complex number. So if this A is a complex number, then you have a real part and an imaginary part. And the real part is the one that actually controls the decay. So if A was complex, that is, A is some alpha plus j beta, then same tests as these. So same tests apply to real part of A. Implying real of A is simply alpha, and the imaginary part, whereas the imaginary part only produces oscillations oscillations only produces oscillations implying E j beta t by Euler's identity is cosine of beta t plus j, maybe I write plus minus here, plus minus j sine of beta t. This is the Euler's identity. Euler's identity. So you can see if alpha is 0, you only have a sine or a cosine going like this, right? And if alpha is some negative, so you have a decaying exponential that goes like this, right? So this is when alpha equals 0. This is when alpha is negative. And if you have a growing exponential, then it is like this. This is like this. So your signals are actually increasing, and this is the case where alpha is greater than 0. And when alpha is greater than 0, obviously you have an unstable system based on this one. But what is this alpha actually? So if you recall from your circuits course, you have this Laplace transform. This is sigma, this is j omega. And if you are in the left half plane, which means your sigma, maybe I call this alpha, and this is actually j beta. So when your alpha is in here, when negative, so when it's negative, you have a stable system, and that is what you probably have also studied in the circuits course, that when the poles are in the left half plane, so whether the pole is here by the cross, or the pole is here, so this will produce oscillation. This is only decaying. And obviously, if you are over here, then this is simply oscillation. There is no decay over here. So this is a real pole. These are complex poles. So we know if we have a real equation, the roots, if we have an equation with real coefficients, then the roots are going to be in complex conjugate pairs. So this we probably will also see probably in the third or the fourth lecture when we study complex matrices. And this is a real pole. These are complex poles which appear in conjugate pairs. So this is a complex conjugate pole. So this is alpha plus j beta. This is alpha minus j beta. So this is the beta that causes these oscillations, and alpha is the one that causes this decay. Okay. So decay, let me write it for you. So decay or growth. So growth, this is the growth, this is the decay. So this is the decay. So decay or growth, maybe I make this one here too, like that. So decay or growth is governed by E alpha t. Okay, so let's go back to the matrix case. So we have digressed a little. So the matrix case. So the matrix case is like this. So the matrix case that we have is U of t is V of t, W of t. My matrix U of 0 is 8 and 5. 8 and 5. I think so. It's 8 and 5. Yeah, 8 and 5. And A equals 4 minus 5 to minus 3. Is this right? 4 minus 5 to minus 3. And then we have d of u of dt equals a of u. So this is the equation that we want to solve. So since for the scalar case, we have an exponential solution, so it's just but logical to assume the same is the case when we have the matrix case. So just like the scalar case, look for some exponential solutions. look for some exponential dependence on t. Dependence on t. Okay. So which simply means, which applies, let's say v of t is some y e lambda t. Why? Because this u of t, this u of t is some e, some constant t times u of 0, and this is the constant over here. And y of t is some e lambda t, and w of t is some z times e lambda t. And we'll see what this lambda and y and z are. Or u of t, so this is u of t, v of t and w of t, so this will become y e lambda t into z e lambda t. I can take out e lambda t, so let me take out e lambda t. Inside I am left with y and z, because whenever I multiply a matrix, which, or a vector is a matrix with one column or one row. This is a column vector, so it has only one column. So matrix, whenever we multiply a matrix by a scalar, so all elements of the matrix are multiplied by that scalar. Okay. And this equals e lambda t, and let me call this vector x, where x I define as y and z. Okay, good. So my equation is then, so d of u of dt equals a u. So d of ut is simply the derivative of this vector. So the derivative of this vector with respect to t is going to give me e lambda t into lambda into, these are constants, y z equals a and u. And what is a? A is 4 minus 5, 2 minus 3. This, by the way, is simply the derivative over here, because u of t is e lambda t x. So this is actually lambda e lambda t x. So this is lambda e lambda t, and this is x, equals a, and u is y e lambda t, and this is z e lambda t. If I expand this out, so I'll get y lambda e lambda t, y lambda e lambda t equals 4y e lambda t. So this row, this column, minus 5 z e lambda t, and this one will give me z lambda e lambda t equals 2. So the second row column, 2 times y e lambda t minus 3 z e lambda t. So if I divide by e lambda t both sides, if I divide both sides by e lambda t, so this implies 4y minus 5z equals lambda times y, and 2y minus 3z equals lambda z. If I put this in a matrix form, so this implies this is 4 minus 5, 2 minus 3, y z equals lambda y z, and this is same as this one, which is matrix A. So this is A, this is X, this is X. So what do we have? We have AX equals lambda X, and this is our eigenvalue problem. Right? So this is the eigenvalue problem. this one or this one in matrix form. So there are two unknowns here. So this is unknown, this is unknown. Both are unknowns. So unknowns. So there are two unknowns, one equation, and unknowns, and we say this one is the eigenvalue. This is the eigenvalue, obviously, of A, the matrix A, and this one, this one is the associated eigenvector. So an eigenvector is associated with an eigenvalue. So associated eigenvector. So what is this equation saying? Telling you, this equation is telling you, if you have a eigenvector, or if you have a vector which is transformed by this matrix A, so vector transformed by this matrix A, you get back the vector, but this vector is actually a scaled vector. So the vector is either in the same direction as the original vector. If this lambda is positive, or if this lambda is negative, then the direction of this vector is reversed. So this is what an eigenvalue problem is. So eigenvectors are vectors which, when transformed by the matrix, you get the vector back, a scaled version of the vector back. Whether if the scalar is positive, the vector is in the same direction, but if the scalar is negative, then the vector then the direction of the vector is reversed. So what is the goal? So the goal is of this chapter is to find eigenvalues, find eigenvalues, and eigenvectors, and eigenvectors, and eigenvectors, and use them, Okay. So if you look at this equation, Ax is equal to lambda x, this is a non-linear equation. It's non-linear. Why? Because lambda is multiplied by x. So lambda is lambda times x. It's lambda times the vector x. However, if somehow we can find lambda, if lambda is known, then the equation is linear. Then the equation is linear. Okay, good. And how do we know this? Lambda? And there is one thing more. You need to also specify here, x is not equal to 0. Or maybe I don't specify here, I'll specify later on. So if I try to solve this one, this means, again, the same thing that I did in the beginning of the chapter. If I multiply an identity matrix here, so this is an identity matrix. So identity times x, or identity times any vector, is the vector itself. So identity matrix times x. So this will be Ax equals lambda times I times x. Nothing changes. This thing is still x, or Ax minus lambda times I times x equals 0. So if I take it on this side of this equal to sign, or if I take out x on the right side, I get A minus lambda I into x equals 0. And here we define where x is not 0. So an eigenvector is a non-zero vector. So maybe I write it associated non-zero eigenvector. Associated non-zero eigenvector. Okay. So if x is not 0, if x is not equal to 0, this implies A minus lambda I has to be equal to 0. So what is A minus lambda I? So this simply means the determinant of A minus lambda I is 0, or which simply means A minus lambda I is a singular matrix, And if you recall, if you have a singular matrix, then you have a row of zeros. If you do the echelon form, this has a row of zeros. So singular matrix implies row of zeros in echelon form. A row of zeros in echelon form implies what? This implies you have free variables. You have free variables, and when you have free variables, this implies the null space of A minus lambda I includes vectors, vectors other than the origin. And this is what we want to find. So we have to choose lambda. We have to choose lambda such that the null space A minus lambda I has some null space greater than 0, whose dimension is greater than 0. So the goal is choose lambda such that A minus lambda I has a null space. X is equal to 0 will always satisfy this equation. X is equal to 0 will always satisfy this equation, but this is not going to help us, because a trivial solution will always satisfy any differential equation. So the goal is that A minus lambda I has to be singular, and this is the one that we said in the beginning, that the polynomial. So this will give you, so this determinant of A is going to give you a correct polynomial in lambda, and that is called the characteristic polynomial. So this is called the characteristic polynomial. So this is a polynomial in lambda, which is called the characteristic polynomial. Okay, or characteristic equation. So let me write this again. So if or when A minus lambda is singular, so A minus lambda I, a singular A minus lambda I implies that dimension of the null space of A minus lambda I is greater than 0, and greater than 0 meaning we'll have free variables, implying greater than 0 implies at least one free variable. This is tying this with chapter 2. At least one free variable, or solutions other than x equals to 0, or other than x is equal to 0 exist. Right? Okay, so let's do that. So A is 4 minus 5, 2 minus 3, and then either we do lambda I minus A. So in some texts maybe they bring A on this side. So either you do A minus lambda, or you do lambda I minus A. It's one and the same thing, nothing changes. So don't get confused whether in some text is A minus lambda and in some text is lambda I minus A. It's one and the same thing. So so this implies A minus lambda I is, and this I'm going to just do once because I'm not going to write it again and again. So A minus lambda I is A minus lambda 0, 0. Right? So this is lambda times I, or lambda times I2, or A minus lambda I equals, maybe I write this determinant in this form. This is 4 minus lambda minus 5 to, 4 minus lambda minus 5, 2, and minus 3 minus lambda. So what happens is when you do A minus lambda I, lambda is subtracted from the main elements on the main diagonal. Okay, so this should be equal to 0. So this implies, so you cross multiply these two and then you subtract these two. So this will be 4 minus lambda minus 3 minus lambda minus plus 10 equals 0, or if I multiply this out, so it's lambda square minus plus 3 lambda minus 4 lambda. So plus 3 lambda minus 4 lambda minus 12 plus 10 equals 0, or lambda square minus lambda minus 2 equals 0. And my roots are lambda square I'm not going to write the roots like this. I'm just going to write it, or maybe I write it once. So lambda square minus 2 lambda plus lambda minus 2 equals 0. So lambda take out. So lambda minus 2 plus 1 lambda minus 2 equals 0, or lambda minus or lambda minus 2 into lambda plus 1 equals 0. So this implies lambda 1 equals 2 and lambda 2 equals minus 1. So these are my eigenvalues. So these are my eigenvalues, and there is this test. There is a test that you can do if you, so the sum of eigenvalues, so this for all square matrices. So sum of eigenvalues is actually the trace of a matrix. And what is the trace? Trace is the sum of elements on main diagonal, elements on main diagonal, and I can write it mathematically as this is sum I is equal to 1 to n I, and for this matrix this is 4 minus 3, so which is equal to 4 plus minus 3, which is equal to 1, and this is 2 plus minus 1, which is equal to 1. So this is all right. And then there is another check. So these are the two checks. You should always do these two checks. The other check is, so this is first check, and the second check is the product of the eigenvalues. The product of the eigenvalues is simply the determinant of A. So this is the determinant of A. And what is the product here? So this product is 2 into minus 1. So this is minus 2. And what is the product here? This product here is 4 into minus 3, which is minus 12. So determinant of A is minus 12 plus 10, which is equal to minus 2. And this is the case here, which is equal to minus 2 in this case, which is minus 2 here, and 2 into minus 1 is minus 1. So we'll see in chapter 6 a matrix which has a determinant which is negative, which has a determinant which is positive, is called a positive definite symmetric, positive definite matrix, and one which has a determinant which is either 0 or positive is called a semi-definite. And similarly, if it is negative, then it's called negative definite, and if it is negative and 0, it's called negative semi-definite. So these are the when we do quadratic forms, then we can actually see from the quadratic forms. This is also a check whether your matrix is singular or non-singular. Matrix is singular or non-singular. So, okay, so always try to check your answer. The sum of the eigenvalues is the trace, and the product of the eigenvalues is the determinant. Okay, so let's find the associated eigenvectors. So if lambda 1 is equal to 2, this implies A minus lambda 1I is equal to 4 minus lambda. So 4 minus lambda is 2. So this is 4 minus 2. This is minus 5, I think, yes. And this is 2, and this is minus 3 minus 2. And with this one, so this is equal to 4 minus 2 is 2. This is minus 5. This is 2. This is minus 5. And we want to find this. So if lambda 1 is, then A minus lambda 1I is this, or A minus lambda 1I into x1 equals 0. So all we need to do is find the null space. So this implies x1 lies in null space of A minus lambda 1I. So I want to find the null space. So I want to solve this equation, which simply means I want to do the row reduced echelon form, which is very simple. So I can do, so 2 minus 5. So what I'll do is I'll say minus row 1 plus row 2. If I do that, I'll get 2 minus 5. So minus 2 plus 2 plus 5 minus 5, 0. And then I do row 2. I do row 2 divided by row 1 divided by 2. So this will become 1, and this will become minus 5 over 2. So this implies my x1. So this is the pivot, and x. So if x1 has elements A and B, A and B. So this means, or maybe I do, yeah, A and B is fine. So this is the free variable. So this is the free variable. So I have my answer in terms of the free variable. So this implies x1 equals b. Here I have 5 by 2 because this when goes on the other side of the equal to sign, this becomes 5 by 2 and this is 1. Or for simplicity, or if b if b is not a vector, if b is equal to 2, this implies x1 is simply 5 and 2. So this is my eigenvector. So if x is an eigenvector, so remember this thing, if x is an eigenvector, then alpha times x is also an eigenvector. Why? Then alpha times x is also an eigenvector. Why? Because ax equals lambda x. So if I multiply alpha over here, I multiply alpha over here. So this is a times alpha times x is equal to lambda times alpha times x. So this is still the eigenvector. So this is the vector y, which is multiplying a, and you are getting lambda times y. So obviously, if x is a vector, then alpha times x is an also, if x is an eigenvector, then alpha times x is an also eigenvector. That's why I can just multiply this so that this looks, this is a nice vector instead of working with fractions. Okay, so what about if lambda 2 is equal, so lambda 2 is equal to minus 1 or plus 1? So lambda 2 is equal to minus 1. So if lambda 2 is equal to minus 1, this implies a minus lambda 2I is simply equal to 4 plus 1 minus 5, 2 minus 3 plus 1, and this is equal to 5 minus 5, 2, and minus 1. Minus 2, sorry. 2 and minus 2. Or again, if I do the row reduced echelon form for this one, because I want to find or since a minus lambda 2I into x2 equals 0, this implies x2 lies in null space of a minus lambda 2I. So for that, I want to find the null space of this matrix. So I do the reduced row echelon form again. So 5 minus 5, 2 minus 2, and if I do minus 2 by 5 row 1 plus row 2, I'll get 5 here, minus 5 here. So minus 2 by 5 will give you minus 2 plus 2 0, again plus 2 minus 2 0, and then I do r1 by 5. If I do that, I'll get 1 here, I'll get minus 1 here. Obviously you should do in 2 steps, 1 here minus 1 here. So this is a pivot, so this is a pivot, just like this was a pivot, this was a pivot, and so this implies x2 is equal to, this goes on this side is 1, and obviously this is the free variable, so this is the free variable, which is 1. No need, always we can always put a b with this one. So if b is equal to 1, so let's assume b is equal to 1, so we have this vector over here. Okay, so my matrix of eigenvectors, so matrix, so let me call this one also, define this one. So matrix of eigenvectors, I define this as this is equal to x1, this is equal to x2. We're going to use it in a little while. This is 5, this is what, 5 and 2, this is 5 and 2, and this is 1 and 1. I'm sorry, 5 and 2, and this is 1 and 1. 1 and 1. Okay. So this is some matrix X, which is the matrix of eigenvectors, and we will see in a little while why do we need this one. So eigenspace is null space of a minus lambda I. If this is all right, so now we have the solution. So this implies u of t, which is equal to e lambda 1 t x 1, which is equal to e minus 2t, which is equal to e minus 2t. It's a good practice to take the largest eigenvalue as lambda 1 and the smallest successively as lambda 2, lambda 3, so on, because we'll see why do we want to do that in a little while. E minus 2t is 5 and 2, 5 and 2. Uh, and this is also equal to, so u of t is equal to this one, and u of t is also equal to this one, is equal to e lambda 2t into x2, which is equal to e minus t into 1 and 1. However, since this is a linear system, so principle of superposition applies. Principle of superposition applies. So when we apply the principle of superposition, applies to homogeneous and linear differential equations. So this implies this implies the complete solution. The complete solution is of this form. U of t is equal to C1 e lambda 1t x1 plus C2 e lambda 2t x2. This is my complete solution. This is some of these solutions. So when the input is x1, this is the output. When the input is x2, this is the output. So obviously the sum is the sum of the two. And these lambda 1 and lambda 2, they control the rate of growth and decay. Control rate of growth or decay. Okay. And how do we find C1, C2? For that, we need to go back and see there is this initial vector. So how to compute? So compute C1 and C2. So how to compute C1 and C2? So you know, okay, U of 0 is 8 and 5. So this U of 0, 8 and 5 implies U of 0 equals C1 E2t, E1 into 2 into 0, so this is gone, so maybe I write it, E2 times 0 x1 plus C2 E minus 1 times 0 into x2. So this is equal to 1. This is equal to 1 because exponential raised to power 0 is 1. Or U of 0 is equal to C1 x1 plus C2 x2. But what is C1, C? So how do I write this one? So I can always, this is the same AX equal to B form. So this is equal to 8, 5. So this is my vector B. This is my vector B. This is equal to my S. So, and this is equal to C1, C2. This is equal to C1, C2. And what is my S? My S is, where did I write S? So this is my S, X1 and X2. So X1 and X2 is 5, 2, 1, 1. So if I solve this one, this is very easy to solve. So this implies, so again, I can do the row echelon form. This is 5, 1, 2, 1, 8, 5. So if I want to solve this one, I will do minus 2 by 5 row 1 plus row 2. If I do that, this is the first row remains unchanged. And this will be minus 2 by 5 plus 2, 0. Minus 2 by 5 plus 1. So minus 2 by 5 plus 1 is 5 minus 2, 3 by 5. So this is 3 by 5. And this is minus 8. So minus 16 by 5 minus 16 by 5 plus 5, which is equal to 25. So this is 9 by 5. So this is 9 by 5. And if I do R2 into 5 over 3, if I do that, this will be 5 over 3 becomes 1. 5 over 3, this becomes 3. And then I can get rid of this 1 because I want to do the row reduced echelon form. So I do minus row 2. Obviously, you're not going to do all this in one step. Minus row 2 plus row 1. If I do that, so minus 1 plus 1, this is going to go to 0. Minus 3 plus 8, this goes to plus 5. And then I do row 1 divided by 5. So just caution, don't do that. Never do that everything in one step. And this, we have the reduced row echelon form, pivot here, pivot here. So this one implies C1. So this is C1. So C1 is equal to 1. And this one implies C2 equal to 3. So my answer is, so answer over here is, where is the answer here? So UT, so this implies U of t is E2t x1 plus e minus t plus 3e minus t plus 3e minus t into x2. But what is x1, x2? So x1 is 5 and 2, and x2 is 1 and 1, or and this is u of t, sorry. This is u of t, which is, and what is u of t? U of t is v of t and w of t, because this is one we wanted to solve. So this implies v of t equals 5e2t, 5e2t plus 3e minus t, and w of t, the second row. So w of t is equal to 2 into e2t, 2 into e2t plus 3 into e minus t. Okay. So this is the solution of our differential equation, which we have found using the eigenvalues and eigenvectors. Also, so in some cases, it is much easier to find eigenvalues than computing the determinant. So for example, if A is a diagonal matrix, if A is a diagonal matrix, then elements on main diagonal, on the main diagonal are the eigenvalues, So if you have a completely diagonal matrix, or if you have an upper or a lower triangular matrix, in both the cases, your eigenvalues are the elements on the main diagonal. Main diagonal are the eigenvalues. And for example, if A is, so if A is 3, maybe example is not here, example is here, 3, 0, 0, 2, this implies A minus lambda I. Determinant is simply 3 minus lambda, 0, 0, 2 minus lambda. So the determinant is simply this product. So this is 3 minus lambda into 2 minus lambda equals 0. This implies lambda 1 equals 3 and lambda 2 equals 2. And what are the corresponding eigenvalues? So lambda 1 equals 3 implies A minus lambda 1 I is simply 0, 0, 0, minus 1, right? So this is the pivot. So this is the pivot. So this implies x1 equals, so pivot is the second column, so this is 1 and this is 0, right? Or the other way. Sorry, it's the other way, I'm sorry. So x, this is x, so this is a pivot. So this, sorry, this one is simply saying it's 0 here, and my free variable is actually the first variable over here. So this is 1 and 0. So this is the free variable. and if lambda 2 is equal to 2, this implies a minus lambda 2I equals 3 minus 2, which is 1, 0, 0, 0. So this is the pivot. So this implies x2 equals, so free variable the second one 0 and this one is 0. Okay. One more stop for today's lecture. If A is the projection matrix, A is a projection matrix. If A is the projection matrix, this implies A is equal to half, 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 or this implies A minus lambda I determinant is half minus lambda, half, half, half minus lambda. And again, this is equal to 0. And if again I find the determinant, so this implies half minus lambda whole square minus half square equals 0. So it's not a good idea always to expand it. So what if this, we call this A and we call this B. So this is simply A square minus equals 0. So this means A minus B equals 0 or A plus B equals 0. So if I do that, so this implies half minus lambda minus half equals 0 or half minus lambda plus half equals 0. So maybe I call this lambda 2, I call this lambda 1. So this implies lambda 2 is equal to 0. This implies lambda 1 is equal to 1. And just to check here, so eigenvalues were 3 and 2. So the trace is 3 and 2, which is 5. The product is 6 and the determinant of this one is 6. So let's see here. So here, so the trace is 1 plus 0, so which is 1. So this is a trace, which is 1. And the product is 0 and the determinant of this matrix is 0. So what do you get from this one? So if the matrix is singular, so this is a very important result. If the matrix is singular, which is this case here, if the matrix is singular, this implies one of the eigenvalues is equal to 0. This is a very important result. So if one of the eigenvalues is 0, your matrix is singular and you cannot find the inverse. So what are the corresponding eigenvectors? So if lambda 1 equals 1, this implies, and what is this thing saying? If lambda 1 is equal to 1, this implies Ax equals x because lambda is equal to 1. So if Ax is equal to x, this implies x projects to itself. Because when you transform x or when you multiply x by this matrix, projection matrix, you get back x. So x projects to itself, and this implies A minus lambda 1I is equal to, so half minus 1 is minus half here, half here, half here, minus half here. This is very simple. So if I do the row reduced echelon form, I simply do row 1 plus row 2. If I do that, so this is minus half, 0, 0. So row 1 plus row 2, row 1 plus row 2, 0. And then I do my row 1 multiplied by minus 2. If I do that, this will become plus 1 and this will become minus 1. And this implies x1. So this is my pivot. Goes on that side is 1. So this is 1 and 1. This is 1 and so this minus 1 is 1, and then we have this free variable 1. So this is the free variable. Okay. And what about 2? So if lambda 2 is equal to 0, so this implies Ax equals 0 because lambda 2 is equal to 0, or this implies x projects to 0. So x, maybe this I call x1, x2. So maybe x 2 projects to 0, projects to 0. So where is this x1? This x1 lies in the x1 is in the column space, of A. And where is this x2? This is in the null space of A. So what is the dimension here? Which I'll do in a little while. So let me find this x2. So this implies A minus lambda 2I, which is the same matrix, half, 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 half. Again, if I do minus R1 plus R2, I'll get half, half, 0, 0. And then I do 2 times row 1, I'll get 1 and 1. I'll get 1 and 1. This is the pivot. So this implies x2 equals, this goes on the other side, becomes a minus 1. And this is a 1, which is a free variable. Free variable. So everything from chapter 2 we have over here. So what is my S vector? S matrix. So S matrix is x1, x2, and this one is 1, 1, and 1, and minus 1, and plus 1. And if you recall, this is a symmetric matrix. This is a symmetric matrix. If this is a symmetric matrix, you have eigenvectors that are orthogonal. So symmetric matrix, a symmetric matrix with distinct eigenvalues, with distinct means not the same. So this is 1, this is 0. With distinct eigenvalues implies corresponding eigenvectors, so if you take the dot product of these two products, these two vectors, this is 0. So corresponding eigenvectors are orthogonal. I can easily make them orthonormal by dividing by their length. And if I do that, then this S becomes an orthogonal matrix, by the way, because it's a square matrix and it becomes has columns which are orthonormal. So column space for a projection matrix, column space, which is AX1 equals X1, is filled with eigenvectors. And what is the dimension here? This dimension of column space is R, which is the rank of the matrix, and the null space AX2 equals 0, is also filled with eigenvectors, And what is the dimension here? And the dimension here, the dimension of the null space of A is simply n minus r. So this implies lambda 1 is repeated r times, and this implies lambda 2 is repeated n minus r times. What about this matrix? So if I have this matrix A, I just want to throw some terms at you. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. So obviously the eigenvalues are 1, 0, 0, 1. So we say lambda 1 is equal to lambda 2 is equal to 1. This means algebraic multiplicity of lambda 1 is equal to 2. So this is the number of eigen times. So this 2 means number of times the eigenvalue repeats. And similarly, and lambda 3 equals lambda 4 equals 0. So algebraic multiplicity of lambda 1 or lambda 2 at both is 0. And also since one of the eigenvalues, since one of eigenvalues eigenvalues is equal to 0, this implies A inverse does not exist. Does not exist. And before I stop, uh, if A is a triangular matrix, whether it's an upper or a lower triangular matrix, 1, 4, 5, 0, 3 by 4, 6, 0, 0, half, we know this implies A minus lambda I, the determinant, is going to be 1 minus lambda, 4, 5, 0, 3 by 4 minus lambda, 6, 0, 0, half minus lambda. Again, if I say this is equal to 2, it is equal to 0. So my determinant is simply, if you remember, this is simply this one times this one, or this implies lambda 1 equals 1, lambda 2 equals 3 by 4, and lambda 3 equals half. And all these values reside on the main diagonal for a triangular matrix. So this is a triangular matrix, and for an upper or a lower triangular matrix, the eigenvalues reside on the main diagonal. This is a triangular matrix. And before I end, just a note of caution: for A equals LU, eigenvalues of U are on the main diagonal. However, they are not the same. They are, because U is an upper triangular matrix. However, they are not the same as A's. So that's why the reduced row echelon form is not going to help us over here. And in general, the pivots, diagonal entries, and eigenvalues are completely different. Okay, so this is all we want to do for the introduction part of the eigenvalues. Next time we are going to look at how we diagonalize a matrix, how do we find the powers of a matrix, how do we find the exponential of a matrix. For that, you need to wait for the second and the third lectures. And then we're going to look at similarity transformation. What happens if a matrix is a symmetric matrix? What happens if the matrix does not have a full set of eigenvectors? Then whether the diagonal form is possible or not. And we conclude this chapter by looking at the Jordan form, which we can have for every matrix that does not possess a full set of eigenvectors. So if you have any questions, you can either send me an email, or we can discuss more on Mondays and Wednesdays. Thank you very much.